Hi, I'm Michael, and today I will introduce KrakenOnMem, a Memristor-Augmented hardware software framework for taxonomic profiling. Metagenomic studies, or metagenomics for short, is a set of studies in which we study many species together instead of them separately. The end goal of these studies is to first, of course, better understand the role of each organism in the world we live in, and second, to use this knowledge and improve our lives, for example, by developing new drugs. Now, you may wonder why we want to study species together. Well, two reasons really. First, we cannot colonially culture some species in our labs yet. Even for the limited numbers we can, the process is not cheap. Second, species in an environment usually have complex relations with each other, so that one cannot discover or observe if we investigate them separately. For a super simplified example, take 6 people who have 1 or 2 types of bacteria or viruses in their body. Depending on the relative abundance of each species compared to the other one, 5 of them might be healthy and 1 disease. This is hard to discover if we only examine these bacteria or viruses separately, assuming that is even feasible in the first place. As a side note, it's worth mentioning that humans have trillions of bacteria, viruses, and fungi in their body. In metagenomics, we take a sample from an environment that can be a human body. Then the output of the study will be answers to questions such as whether the sample contains a new species, or do you have a potentially dangerous yet dormant virus in this environment, and why. Taxonomic profiling is a task of determining the existing species and their relative abundance. Therefore, you can see how taxonomic profiling will be the natural first step of any metagenomic study. To visualize the profiling better, this is what the input and output of a taxonomic profiler looks like. Current profilers are computational approaches that work with sequence data, or in other words, strings of ACGT. There are 2 reasons behind this decision. First, the sequencing technologies have advanced significantly in the past decade, so much so that, as you can see in this graph, the drop in the cost of sequencing has surpassed the improvements due to Moore's law. Second, advances in computational powers and the availability of powerful clusters make the computational approaches faster and more economical than lab-based approaches. However, current profilers, although accurate, are still expensive for 2 main reasons. First, these approaches require tremendous caches and memories that do not exist in everyday machines, only in the clusters. And second, current profilers are mainly memory bound, or at least wasting a lot of time and energy on their data movement. Therefore, we now use expensive clusters inefficiently, which translates to high costs for metagenomics and delays the process. An ideal taxonomic profiler, therefore, has high accuracy, high performance, low memory requirements, high energy efficiency, and low cost. There has been significant effort into improving profiling performance through efficient heuristics and computational approaches. However, although these approaches address the computation overhead in taxonomic profiling, none of them neither target the common operational bottleneck of profilers nor alleviate the data movement overhead. Our key idea is to accelerate the main bottleneck or operation of almost all today's taxonomic profilers, which is the table lookup operation. We do this through a one-cycle exactly matching keys and data retrieval for our table, and by exploiting the analog computing capabilities of emerging memory technology. However, performing table lookup efficiently in one cycle inside memory can be challenging due to large hash tables that metagenomic databases work with and do not fit into the caches at various levels. It is also challenging due to the requirements for supporting different tables for various databases. And finally, such a design is challenging due to the limited hardware resources in memory systems. To this end, we propose KrakenOnMem, the first Memristor-Augmented processing system designed for taxonomic profiling that is accurate and reduce the data movement overhead and avoid underutilization of cache hierarchies, or in other words, large memory requirements. KrakenOnMem provides high performance and energy benefits compared to the state-of-the-art hardware and software based. Now, with a summary of my talk, let's start with some background so that we can dive into the work in more detail. First, a brief background on taxonomic profilers. There are two methods to profile sequence data: alignment-based and heuristic-based, or non-alignment. As the name suggests, in the alignment-based method, we first perform an alignment among each read and each possible reference genome, and then we assign the read based on the result. Methods in this category are costly, as a single alignment has a high cost, especially when we consider the fact that we need multiple alignments per every single input. They do not necessarily produce accurate results and require post-processing in addition to alignment, as short string can map to multiple reference genomes anyway. Alignment-based profiling, however, does not demand high memory requirements. In heuristic-based method, on the other hand, we first create a histogram or similar data structure for each reference genome. Then a similar data structure is built for the input, and finally we compare it with those for references. These methods can be a little less accurate than the previous one. They also require more memory and RAM to store and work on their data sets. However, heuristic-based methods provide higher performance than alignment-based ones due to the elimination of the alignment. And that's why usually today's profilers are heuristic-based. Kraken 2 is a state-of-the-art heuristic-based taxonomic profiler in metagenomics. In Kraken 2, one first builds a hash table with seeds and keys and taxon labels as values. A quick background: in genomics, seeds or k-mers are widely referred to as short strings, 32 characters max. You can think of taxon labels as a species of references to which the seed belongs to. In Kraken 2, these labels are usually called as LCA, standing for lowest common ancestor in the tree structure of taxonomic rank. Then whenever an input comes, Kraken 2 first extracts the seeds of the same size, queries the hash table, and find the associated taxon label. By adding all the retrieved taxon labels, the abundance estimation of the read is achieved, of course, after normalization. As I alluded to before, currently, Kraken 2 is the most widely used state-of-the-art taxonomic profiler. I want to quickly note that we typically use Kraken 2 with Kraken, which is an orthogonal method to Kraken 2 that we apply as post-processing to improve profiling accuracy. This combination, or Kraken 2 in particular, provides high accuracy, fast profiling, and reasonable memory utilization. Now let's switch quickly to the PIM paradigm and define that one as well. First, as a motivation, previous work showed that more than 60% of system energy is spent on data movement, and a similar percentage holds for the performance of data-intensive applications. Therefore, the processing in memory paradigm, or PIM, has emerged. In PIM, we look at the memory as a conventional accelerator and perform some operations inside the memory, where the data resides, and prevent unnecessary data movement by doing so. This way, we accelerate operations or kernels that require a lot of data, but not much computation. This picture gives a high-level overview of the mindset behind PIM, or at least most of the PIM design. PIM paradigm offers some advantages compared to the typical von Neumann-based architectures, in which memory and compute units are separate. The first one is the high parallelism it provides. The idea behind this advantage is that perform some vector-based operation within memory tiles, banks, ranks, and etc. simultaneously, you will achieve the high parallelism that is usually desired. The second advantage is the high energy efficiency a PIM-enabled design offers. Last but not least, PIM-enabled design typically offer logic and arithmetic operations on long vectors in one cycle as well, which is very useful. So far, both academia and industry have investigated PIM-enabled methods for different memory technologies, different operations, and also different applications. The last background piece is Memristor devices, or Memristors for short. Memristors are non-volatile emerging memory technologies that store the data in form of their resistance level. PCM and STT-MRAMS are just two examples of these technologies. Memristors inherently follow Kirchhoff's law, and therefore, with an array structure that is typically for memristors, they can offer vector multiplication operation in one cycle, or VMM for short. As seen in this picture, with some intelligence or at least unconventional mapping and applying data in and to the memristor-based arrays, respectively, one can significantly improve the complexity of a vector of a matrix multiplication. Previous works also show that the memristor can perform bulk bitwise operation both inside and outside the periphery of an array. STT-MRAMS, which stands for Spin Transfer Torque Magnetic RAM, is a memristor-based technology that currently is known as one of the leading candidates for PIM-enabled architectures and next-generation memories. This is because STT-MRAM-based devices have shown great scalability compared to alternatives, near zero leakage power, and lower power consumption. However, we use STT-MRAM for our design due to our accessibility to real measurements and accurate memory models for larger scale simulation, and not because they have a specific characteristic that separate them from this design being applicable to other alternative memristor-based designs. In other words, in theory, other memristor devices should be useful for the design proposed in this work as well. However, we have not explored them yet. In this section, we present the results of experimental studies conducted to understand the potential bottlenecks of Kraken 2 for improving profiling performance. We also briefly discuss why previous PIM-enabled designs are not suitable to address our problem. We analyze the execution time of Kraken 2 on real-world genomic read datasets and configuration. We break down Kraken 2 into four main essential functions: building the taxonomy tree, key extraction, table lookup, and profiling. The first one, building a taxonomic tree, is a one-time job for a reference data, but the other steps repeat for each new input. It is worth noting that all other taxonomic profilers that we have currently also have similar or equivalent functions. As you can see in this figure, we observe that the table lookup operation dominates the execution time of Kraken 2. Therefore, we conclude that in an ideal version of Kraken 2, this overhead of lookup operation should be mitigated to a minimum necessary. We also want to briefly note that no previous work that really target this operation, especially in taxonomic profiling. The closest recent work we found is Steve, presented in ISTA 2021. Steve is an IndiRAM accelerator for K-mer or seed matching. However, we have identified four limitations for Steve if applied directly to taxonomic profiling. First, Steve comes with a huge area overhead of more than 10%. This overhead most likely prevents Steve production and is directly in contrast with the low cost of the objectivity of our problem. Second, Steve incurs high number of write operations due to the duplicate inputs that the design requires for matching. Third, Steve has a significant amount of internal data movement exacerbated in taxonomic profiling due to the large data set it works with. Finally, Steve is only applicable to DRAM, and none of the existing or future emerging memory technologies can benefit from its idea. Motivated by our observation, our goal is to design a Memristor-Augmented PIM-enabled accelerator for cost-effective table lookup required in taxonomic profilers of Metagenomics. We have three objectives in designing our new system. First, the system should provide high performance for table lookup and end-to-end profiling. Second, the design should be applicable for different reference databases, or in other words, tables with varying sizes for keys and values. Third, it should not require significant hardware overhead. To this end, we propose KrakenOnMem, which is the first PIM-enabled processing system designed for taxonomic profiling. Our key idea is to perform the table lookup of hash tables that are too big for cache hierarchies inside the memory and send the retrieved labels to the host system for further processing. Basically, considering a typical system, we want to perform this step 5 inside our PIM-enabled memory. By doing this, the new distribution of responsibility in our system will look like this, where we add a component called PLPIM for performing our operation. However, performing the table lookup inside the memory can be challenging due to the different lengths that keys or values of varying reference databases have, and also due to the limited hardware resources that one can expect from a PIM-enabled accelerator. For successful table lookup operation, the TLPIM needs to be able to perform 2 operations at least: key matching and label retrieval. So if you consider this figure as an overview of KrakenOnMem, then our TLPIM component has 2 types of memory arrays to handle these required operations, namely key arrays and LCA arrays. Moreover, TLPIM has also a controller that acts as a mind behind it. Note that these 2 types of array in TLPIM, key arrays and LCA arrays, are identical from the hardware perspective, making them more suitable for being considered in future design. Let's take a closer look at the key arrays, which are responsible to store the keys where the reference hash table and from the reference hash table, and then they are also responsible to perform the matching operation. After considering several possible data mappings and matching options, we decided on column major data alignment for the keys. We also decided to use Memristor devices directly to store the program, to store or program their reference keys. This picture shows our mapping in a nutshell. But to understand our matching mechanism and its relations with our data mapping better, assume we use Q for an input key and K for a reference key. The Q bar and K bar are their corresponding complements. Now we program a column with a vector KK bar, which is K concatenated with K bar. Then we apply the vector Q bar as an input to the memory array. This way, based on Kirchhoff's law, we have the results of Q XOR with K reaching our sense amplifier as a current. If we modify the sense amplifier so that it can determine whether this current is higher than the current equal to the length of the key multiplied by unit current, then we effectively perform the pop count of our XOR result in one cycle. This change in the reference of sense amplifier is reasonably easy task to perform and has been done in context of analog computing so many times already. So this design can provide a key matching in one cycle inside the memory, which was desirable and targeted in the first place. There are 3 points we want to highlight regarding our proposal for key arrays. First, this method doubles the required memory cells for reference keys. However, this is acceptable as programming the array for reference keys is a one-time task compared to our always changing input. Moreover, our evaluation showed that the achieved improvements are more than doubling all the resources in the baseline. Also, it's worth noting that by doubling the keys, we are not doubling the hash table size or even making it 1.5 times bigger, as the keys are typically much smaller than the taxol labels in our application. Second, unlike previous design that requires ADCs or analog to digital converters in their for their vector matrix computation, our method works still with the sense amplifier. This simplification is because a key array does not need to get the exact number of the matches. We simply interested in whether there is a match at all positions. Analog to digital converters represent a significant area overhead compared to memory cells. Therefore, the current design overcomes a critical source of inefficiency that exists if one applies previous work design for this purpose. Third, in theory, The same result can be achieved using content addressable memories with CAMs, but not TCAMs. However, in the memory cells in CAMs are different and fixed and cannot be reconfigured for other types of memory arrays. In other words, one cannot reuse key arrays for other memory units if they use CAM for matching. Such a choice limits the design. For example, for a case where one wants to support and load different reference tables, this is particularly needed in metagenomics, where CAM's controller is more complex than the normal memory controller required in the proposed design. For retrieving taxonomic label, we use LCA arrays. The data mapping in these arrays is row major, unlike the key arrays. This means that we program our Memristor devices in one row to contain the lowest common ancestor label of a reference string. This figure shows what our proposed data mapping for LCA arrays look like. Yes, our LCA array, however, applies a revised data mapping, allowing the design to retrieve the label in one cycle. This mapping is needed because of the limitation of shared sense amplifier among columns in emerging memories. In these technologies, the memory cells are significantly smaller than the size of a sense amplifier. Therefore, to not waste the area and maintain the cost advantage of emerging memory technologies, we typically use fewer sense amplifier or digital converters than the number of columns, and use time multiplexing techniques to read out the whole row. To overcome this limitation, LCA arrays store the interleaved LCA labels as shown in this figure. This way, we allow the LCA arrays to read all the bits that belong to one label simultaneously. I want to note that the ratio between the number of LCA arrays and key arrays is not necessarily one-to-one. In fact, three arrangements are possible, as one can imagine. The first one is when we have one key array feeding to more than one LCA array. The second possibility is when there is indeed a one-to-one connection. And the last one is when we have one LCA array per multiple key arrays. The ratio for the highest performance highly depends on the number of sense amplifiers per key array, length of the LCA labels, the capacity of the sense amplifier in an LCA array, and number of sense amplifiers per LCA array. In other words, it depends not only on the device characteristic of memory arrays and their peripheries, but also on the length of the values or labels in the reference table. This is the main reason that having the compatibility between key arrays and LCA arrays is necessary. And we use a typical memory layout for both key arrays and LCA arrays instead of CAMs for key arrays. Now, let me briefly mention some other designs or engineering optimization that currently KrakenOnMem is benefiting from as well. First, we only require a network among corresponding key arrays and LCA arrays. Basically, as long as we manage to connect arrays in the same bank in a traditional memory architecture, we do not have any additional network requirement for our PIM-enabled memory. Therefore, we consider the minimum necessary network for our area estimation and controller design in the large-scale simulation. Second, in KrakenOnMem, we do not broadcast the input keys. By sorting the table in the first place based on the keys and using a small index table with the first few bits of every key, the controller can send the results or keys basically to be processed only to the arrays that there is a match possible. Third, we applied power and clock gating to ideal arrays. Unfortunately, due to the limitations of current PCIe connections, we cannot always utilize the TLPIM fully. In other words, we may send fewer keys to be queried in different key arrays than TLPIM can handle. You can find out more about these optimization and potential future works for improving KrakenOnMem or building on top of it in the paper. And now for our results. We evaluate the following systems. Baselines are state-of-the-art software or hardware taxonomic profilers. KrakenOnMem is basically Kraken 2's implementation integrated with our TLPIM unit. And we evaluate our design and baseline profiler on synthesized design using TSMC 28 nanometer for TLPIM and clusters with large memories and using various real data sets. For more details about our methodology, please refer to the paper. We analyzed the benefit of TLPIM and KrakenOnMem for 3 real metagenomics datasets. We show that these benefit in software and hardware designs in this figure. TLPIM and KrakenOnMem provides on average more than 1,300 times and 61% speed up for table lookup and end-to-end profiling respectively compared to the software baseline. They also provide on average more than 110 times and 1% speed up for table lookup and end-to-end profiling respectively compared to the hardware baseline. To evaluate the applicability of TLPIM and our optimizations for other profilers, we also analyze the benefit of applying TLPIM, a modified version of it actually, for K-mer counting and then meta-align on our 3 metagenomics data. We show these benefits in software and hardware designs in this figure. And as you can see, our tweak TLPIM and corresponding meta-align based method provides on average more than 1,500 times and 23% speed up for key counting and end-to-end profiling respectively, compared to meta-align's original counting mechanism, KMC, and meta-align itself. This is significant because table lookup wasn't even the main bottleneck in this application. However, our design with a bit of modification is still applicable to this type of profiling class as well. We also evaluate the memory utilization of our data mapping on different array configurations. Our system model showed that KrakenOnMem achieves up to 99.6% memory utilization for key arrays and achieves up to 70.8% memory utilization for LCA arrays. In this paper, you can find out about other results as well, such as energy and power consumptions of KrakenOnMem. They required additional area for KrakenOnMem. Energy saving of TLPIM compared to Steve for table lookup, and some more discussions over Steve in the context of taxonomic profiling. And finally, possible future direction for KrakenOnMem to be improved or built upon. Now, let me conclude by giving a summary. There has been a significant effort into improving profiling performance through efficient heuristic and hardware accelerators. While these approaches address the computational overhead and high accuracy requirements of profilers, none of them utilize their hardware infrastructure efficiently or alleviate the data movement overhead. Our goal is to improve the performance, energy efficiency, and scalability of taxonomic profilers by efficiently exploiting analog computing and reducing unnecessary data movement. The key idea is to perform table lookup operation of large hash tables that do not require expensive computation in memory systems of emerging technologies to fundamentally reduce the data movement overhead. However, table lookup inside memories is challenging because large hash tables of target database cannot fit inside caches. Such a design should support hash tables with variable size keys and values, and there are limited available space for additional hardware resources in memory systems. To this end, we propose KrakenOnMem, the first hardware software co-design framework designed for taxonomic profiling to improve the performance and reduce the data movement overhead. KrakenOnMem provides high performance and energy benefits compared to state-of-the-art hardware and software baselines at a low cost. That concludes my talk. Thank you very much for listening, and I look forward to discuss with you this project and the future ones in the conference. Thank you very much.